Okay, we're going to be looking at a couple different methods for multiplying vectors. And the first method that we're going to look at is called the dot product. And the dot product, given two vectors v and w, we write v, and it looks like a multiplication sign, so we're going to need to be careful. But we say v dot w. And the idea of the dot product, well, first of all, the result of a dot product is a scalar. So when you dot v with w, and that's the language that you use, I dot v with w, you're going to get a number back. So it doesn't give you a vector back. And the idea of the dot product, what it does is it says, okay, let's imagine, again, we have w and v. The idea is it says we are going to multiply the magnitude of w. So we're going to multiply the magnitude of w that's in the v direction. And we're going to multiply that by the magnitude of v. And for now, we're just looking at a process. This is used application-wise. It's used all of the time in physics and other sciences, but primarily physics uses the dot product all of the time. So there's two different definitions that we're going to be using. The geometric definition, which says that given v and w and some angle theta between them, that the dot product is the product of the magnitude of v and the magnitude of w times cos of theta. And just to make sure that we see how this definition that I gave before and the geometric line up, w cos theta is this blue vector right there. That's w cos theta. So it's multiplying the magnitude of w in the direction of v times v. Okay, and then the algebraic definition says that, well, if we just multiply all of their components, so the x components and the y components and the z components, find the respective product of the components and then add them, you will get the dot product. All right. So it says find the dot product using both methods of v, and that's a dot w. If 3i plus 3j plus 4j, if v equals this and w equals that. Well, the first method that we'd want to use here, the easiest method, is the algebraic method. So the algebraic method is multiply the i's together and then multiply the j's together, and we get 15 plus 48, and we can add that further to get 63. And that's saying that's the product of well, let's draw out what these look like and talk about what that means. So v is something like that. So over 3 up 4, that's v. And w is over 5 up 12. So something like this. So if we say v dot w, what that's saying is it's multiplying the magnitude of v. So it's multiplying the magnitude of v cos theta, so in the direction of w, times w, times the magnitude of w. Okay, so the first method here, clearly that's easier, is the algebraic. And the reason why that's easier than the geometric is for the geometric, we're going to need to get this angle theta. So the idea to do that, well, we know that if we call this angle here theta 2 and this angle theta 1, then the theta that we're looking for is theta 2 minus theta 1. That's this angle right in there. That's the angle between them. So theta 2 is tan inverse of 12 over 5 minus theta 1, which is tan inverse of 4 over 3. And we get that equals, and of course we're going to need to use our calculator for this. So second tan 12 over 5, and I'm going to make sure that I'm in degrees. Second tan of 4 over 3. So we get that it's 14.25 degrees. Okay, so to use here's the algebraic. To use the geometric model then, or the geometric method, it's going to be magnitude of V times the magnitude of W times cos of 14.25. And we know that magnitude of V, because it's a special 3, 4, 5 triangle, is 5 times the magnitude of W. It's a 5, 12, 13 triangle, so 13 times cos of 14.25. And we should get the same answer back. And let's cross our fingers here, take out the calculator. We have 5 times 13 times the cos of the second answer that we just had, and we get exactly 63 back. And that's as we should expect. Regardless of the method you use, you should get the same answer. All right, well, here are a couple important properties of the dot product. The first is that the multiplication of two products, or of two vectors being dotted, is commutative. In other words, v dot w and w dot v will result in the same thing, and that makes sense because consider v and w and the angle theta between them, and remember that v dot w is magnitude of v times the magnitude of w, and both of those aren't going to change if I change the order, because w dot v is going to be magnitude of w times magnitude of v times cos of theta. And so it's clear by looking at the geometric proof that cos of theta stays the same, and it doesn't matter the order in which we multiply these scalar magnitudes. And then that's the first property. The second property is that if we multiply a vector by some scalar lambda, so v dot lambda theta, we can pull the lambda out in front, or we can associate the lambda with the v. It doesn't make a difference there. So in other words, let's say I have 2 times vector v dotted with vector w. This is the same thing as 2 times v dot w, and it's the same thing as 2 times w dot v. So the order in which we multiply a scalar doesn't matter. And lastly, we can distribute a dot product over addition. So v plus w dot u, we can distribute that dot product to get v dot u plus w dot u. And the last major, really important property is that if we've got two vectors, v and w, they're said to be perpendicular, or the other word is called orthogonal, if the dot of the two vectors equals 0. And that makes sense because, consider two vectors that are perpendicular. Well, if they're perpendicular, we know that the angle between them is theta, and v dot w corresponds to magnitude of v times magnitude of w times cos of theta. And cos of theta, if it is in fact perpendicular, we've got cos of 90, and cos of 90 we know is 0. So this ends up being 0. So provided that they're perpendicular, and the other word that you should know being orthogonal, if the dot of two vectors equals 0, that proves that they're perpendicular or orthogonal. So let's think about a couple different questions. We've got v dot v. So think about that. It's like a vector v. Ooh, let's get out of that. It's a vector v dotted with itself. So what's the angle between them? Well, the angle between them is 0. So v dot v is going to equal magnitude of v times the magnitude of v times cos of 0. Well, cos of 0 is just 1. So this is going to be the magnitude of v squared. Okay, what about these? That's the first one. What about these next three? Well, the next three, we've got I dot k. That's going a unit vector in the I direction and a unit vector in the z direction. Well, we know those are going to be perpendicular, so it's going to be 0. J dot k is in the y and in the z, again perpendicular, so 0. And I dot j is in the x and in the y, perpendicular, so 0. All right, so let's think about this. This says, suppose the vector b is fixed and has length 2. The vector a is free to rotate and has length 3. What are the maximum and minimum values of the dot product a dot b as the vector a rotates through all possible positions? What positions of a and b lead to these values? Well, so we're looking at a dot b, and we know that that equals magnitude of a times magnitude of b times cos of theta. B is fixed, so let's put b like this, and a, and it has a magnitude of 2. And a could be here or anywhere in a circle. So when will it be biggest? Well, it's going to have a max value when cos of theta equals 0, because that's when cos of theta is its max value. When cos of theta equals 1, which means that theta equals 0. So when cos of theta equals 1, which is when the angle between them is 0, so at this point right here, the dot of a dot b will equal 2 times 3 times cos of 0, which equals 6. And the minimum value is when a has rotated all the way around to be over here, when theta equals pi. Because at that point, at cos of pi, we get -1. And that's the most negative it can be. So at that point, a dot b will equal 2 times 3 times -1, which is -6, which is the minimum value. And as far as if we're thinking about like the absolute value, if we're thinking about the absolute value of the dot product, so the absolute value of a dot b is a minimum. So it's a min at at theta equals pi over 2 and 3 pi over 2, because at that point cosine of pi over 2 equals 3 pi over 2, which is 0. So the dot product there will be 0. So again, the idea of the dot product is it is multiplying vectors in their same direction. All right, so it says, in the next question, we're thinking about ideas of orthogonality. So it says, which pairs from the following list of three-dimensional vectors are perpendicular to one another? Well, to do that, if they're perpendicular to one another, their dot product must be 0. So if we look at u dot v, and now we're going to be using the algebraic method, it's going to be looking at the I values, 1 times 1 plus, now looking at the, well, this has no j value and this does, so plus 0 times root 3 plus root 3 times 0. This equals 1, so u dot v equals 1. Therefore, they are not perpendicular because the dot product doesn't result in 0. What about u dot w? So looking at their components, we've got 1 times root 3 plus 0 times 1 plus root 3 times negative 1. And if we add those up, this is 0. So therefore, we know that u dot w is 0. So u is perpendicular to w. And the last case, v dot w. V dot w equals, looking at their components, 1 times root 3 plus root 3 times 1 plus 0 times negative 1, and this does not equal 0, so therefore they are not perpendicular. So the dot product presents us with a wonderful opportunity of testing for whether or not vectors are perpendicular or orthogonal. All right, now let's develop a really important identity that looks at how we can find and define equation of a plane given a normal vector. So a normal vector, just to be clear, if we've got some plane, a normal vector is a vector coming out of the plane that's perpendicular to the plane. So this is a normal vector. And that dotted line is the idea of like going into the board or into the screen, and the solid line here is going out of the screen. So it's perpendicular to the plane. So let's imagine we're just going to define that normal vector to be AI plus BJ plus CK. So it's defined as such. And let's say that we've got a fixed point on our plane. So let's call this point here the point x naught, y naught, and z naught, and we'll call it this point here. And then we've got some variable point. So any point here, p. So this was p sub 0. So now we have some point here, p, and we're going to say that p equals x, y, z. All right. So then we could get the vector p naught to p. So this is this vector here, and that vector would be x minus x naught I plus y minus y naught j plus z minus z naught k. So we already know how to find that's a displacement vector. And now here's the big thing. So if we're defining n to be a normal vector, and we now have this displacement vector that's contained in the plane, and that's key, that's in the plane, and we've got our normal vector to the plane, well, if we dot the normal vector times our displacement vector, which is in the plane, it's going to be equal to 0. And that's because the normal vector is perpendicular. Normal is perpendicular. That's just the definition of it. So therefore, using our algebraic method for a dot product, we have that the dot between those should be a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And that dot product should equal 0. And this gives us an equation for a plane. This gives us the equation for this plane here. And what did we need to get that equation for the plane? Well, we needed a normal line, so a line perpendicular to the plane, and a point on the plane. So given these two things, a normal line and a point on the plane, we can find the equation for a plane. And this is big. This is a huge new idea. So let's look at an example of that. Actually, let's first summarize this a little bit. The idea being the equation of a plane given their normal vector, so just like we looked at before, containing some point, is the following, and it's equal to 0 because when we dotted them, because they were perpendicular, they're equal to 0. And therefore, if we want to simplify this, we could write this as ax minus ax naught plus by minus by naught plus cz minus cz naught, and that's equal to 0. And then what we're going to do is we're going to say, let's let ax naught plus by naught plus z naught plus cz naught equal to d. So in other words, this and this and this, the sum of those equals d. So we get ax plus by plus cz minus d equals 0. And then we can write that in the form ax plus by plus cz equals d. And this is a nice form because it's just in terms of all of their respective slopes set equal to some constant. Okay, so now we'll look at an example of this. So in the next example, we're going to be given a normal vector. So we've got our normal vector here, and listen to the language. It says find the equation of the plane that's perpendicular to this vector. So therefore we know that the normal vector is negative I plus 3j plus 2k, and we're going through the point 1, 0, 4. So the equation for the plane, if we dot them, we're going to get, well, we don't even really need to dot them because we can just use our formula. We get negative x minus 1 plus 3 y minus 0. So just to be sure, the negative, the 3, the 1, the 0, plus 2 z minus 4, and this has to equal to 0. And if we were to simplify this, we get negative x plus 1 plus 3y plus 2z minus 8 equals 0. And simplifying that further, negative x plus 3y plus 2z equals 7. So whether you want to put it in this form or this form, both are adequate equations for the plane that contains this point and is perpendicular to that vector. Working the other way, we can say, well, let's find us a normal vector to the plane. So we want to find the normal vector to the plane with this equation. Well, if we look at A, we've got x minus y plus 2z equals 5. And I'm going to put 1 here. And what we recognize is that the coefficients from our plane must be the coefficients from the normal line. Because remember, given the normal line, AI plus BJ plus CK, the plane had the equation A, x minus x naught plus B, y minus y naught plus C, z minus z naught. So all of these were the coefficients, C, B, and A, which came from our normal vector. So for part A, our normal vector equals I minus j plus 2k. And in part B, well, B is a little bit different because we've got z over there, so we need to rewrite part B as 0 equals 0.5x plus 1.2y minus z. So then we get that the normal vector must be 0.5i plus 1.2j minus k. Okay, well, while it's most simple to think about the dot product in 2 dimensions or 3 dimensions, and it's easy to think about the dot product in 2 or 3 dimensions because we can think about the angle between them, we can also think about the dot product in n dimensions, where n is pretty much infinite, where it is infinite. And if we're talking about in terms of n dimensions, we can use the algebraic definition, which says to dot u and v together, all we need to do is multiply the corresponding components of u and v. So we'd get u1 v1 plus u2 v2 plus dot 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 all the way to un vn. So an example of this below says a video store sells videos, tapes, CDs, and computer games. So we've got 4 dimensions. And we define the quantity vector Q to be Q1, Q2, Q3, Q4, where those are the quantities sold of each. And the price vector, P, is the price per each item. So Q is the quantity, P is the price. Well, what do you think P dot Q would be? Maybe pause the video and think about what that would be. Well, in terms of the dot product, it's Q1 P1 plus Q2 P2 but what are each of these? Well, Q1 P1, that's the quantity of videos times the price of videos. So that's my revenue from videos. And Q2 P2 is my revenue from tapes. So this whole thing is my total revenue, because it's how much I'm selling each item times the price of those items. So there's a nice little application of the dot product. Okay, one of the things that we will often want to do is something that's called resolve a vector into components. And this idea is given the term projections. So we're going to be projecting a vector onto another vector. Well, what do we mean? Because we've actually done projections before. In the past, what we've done is we've said, okay, let's imagine some vector, let's say some vector v, which is 3i plus 4j, and it's some vector that looks like this. And what we've done is we've said, well, this is, we could think about this as being 3 in the I direction plus 4 in the j direction. And this idea, what we've done is we've projected our vector v onto the x-axis here and onto the y-axis right there. Similarly, let's say that we have some vector w here. This is u, and then we've got another vector v. What we can do is we can project v onto u. So this red vector here is the projection of v onto u, and that's the v. That's the amount of v that's, how do we write this, parallel to u. And then in black, here's our perpendicular v. So that is the v that's perpendicular to u. All right, so this is something that we're going to be wanting to do, and we can do this using the dot product. So the idea, the projection of v on u, which we call v parallel, is measuring the distance of v that's in the u direction. And another word instead of projection, we say it's the shadow on u. You know, if we think about like some light up here and shining down on v, well, that is V parallel, which is the shadow of V onto U. So V parallel is in the direction of U. Well, if it's in the direction of U, what's going to give us the direction of U, the way that we're going to find the direction of U, is to use the unit vector in the U direction. So U over the magnitude of U is a little unit vector in the U direction. Well, and what about the magnitude? What's the magnitude of V parallel? Well, the magnitude of V parallel, we know that. That's the dot product. The magnitude of V parallel is U dot V, which equals magnitude of U times magnitude of V cos theta. Therefore, the equation, and see if you can get this, maybe you can pause the video and see if you can take a stab at what you think V parallel is. Well, V parallel has a magnitude of U dot V, and it's in the U direction. So times, and remember, this is just a scalar, so times U over the magnitude of U. Well, simplifying, the magnitude of U goes away, and we get that V parallel equals the magnitude of V cos theta, and that's just a scalar, times our vector U. And that tells us, that gives us V parallel. So that's a vector that's in the U direction that is the projection of V onto U. So we have that rewritten again here, just that V parallel, and this is what we just derived. Okay, well, what about V perpendicular? How are we going to find that? Well, let's think about that. Take a stab and maybe pause the video and see if you can find V perpendicular. Well, the idea of V perpendicular is that, again, here we have our vector, we'll call this our vector V, and here is U. So vector, this is V parallel, and this is V perpendicular. We know how to find V parallel. We know that V parallel is just V dot U times U, and V we know. So how can we get this? Well, it's in the screen above, so maybe you could just get it through there. Or what we can do is think about adding vectors. If we do V parallel plus V perpendicular, so if we add these two vectors together, the sum of those vectors is exactly V. So we know how to find V parallel. V is going to be given to us. So to find V perpendicular, it's just V minus V parallel. So now we can get both perpendicular and parallel components of v onto u. All right, well let's see an example of that. So we've got a force and a velocity vector here, and to draw them, our force vector 4I plus j. This is our force vector, and our velocity vector is 3I plus 4j, so something like this. And what we want to do is find the components of f parallel to v. So we want to find this f parallel to v, and then we're going to want to find f perpendicular to v. So first, f parallel, meaning the force that's in the same direction as the velocity. Well, what we need to do is we need to express our velocity vector as a unit vector. So a unit vector in the v direction equals v over the magnitude of v, which is 3I plus 4j over 5, so 3/5 I plus 4/5 j. So that's the little unit vector in the v direction. And so just as a reminder, now that we've got a unit vector in the v direction, going back a couple slides, we know that v parallel will be v dot u times u. So f parallel will equal 4I plus j dot 3/5 I plus 4/5 j multiplied by 3/5 I plus 4/5 j. In other words, we're dotting our f with our unit vector in the v direction, and then we're multiplying it by our unit vector in the v direction. Okay, so what do we got there? Well, if we simplify that, looking at the top piece, we've got 12/5 plus 4/5 multiplied by 3/5 I plus 4/5 j. And doing a little bit of work with fractions, we can now get that this equals 16/5 times 3/5 I plus 4/5 j, and now we distribute to get 48/25 I plus 64/25 j, and that is f parallel. And f perpendicular, well, we know that f perpendicular, if we go back a couple slides, is just f minus f parallel. So, using this idea right here, so therefore we get that f perpendicular equals 4I plus j minus our f parallel. So 48/25 I plus 64/25 j. And without doing much simplification, f perpendicular is just 4 minus 48/25
I plus 1 minus 64 over 25ths j. And there's my force that's perpendicular to the velocity. Okay, and that is it for now. There's a couple problems after this, but I think we've done enough for you to have a really good ability to get started on this assignment.